Welcome to our departmental seminar. Does everyone online can hear me? Just a thumbs up from someone. Yeah, okay, many thumbs up. Thank you. Thanks everyone for joining the Informatics departmental seminar. Today is our great honor to have Professor Samson Abramsky for our departmental seminar, who accepted our invitation. Professor Abramsky is a professor of computer science at University College London. He has held chair positions at Imperial College, the University of Edinburgh, and Oxford University in the past. And he's famous in the area of computer science and beyond for his extensive contributions to the logic and semantics of computation, and more recently also in the mathematical foundations of quantum computation. He has many awards and many distinctions, many in his career. He has received the EATCS award, the Lovelace Medal, the Alonzo Church Award, and 3 Leaks Test of Time Awards. He's a fellow of the Royal Society, fellow of the Royal Society of Edinburgh, a member of Academia Europaea, and a fellow of the Association of Computing Machinery. So he has many distinctions and accolades. I can continue for a long time, I think, but I think it's better for everyone. We're really looking forward for his talk, which will be about the logic of quantum paradoxes. A very exciting title, and we really look forward to the talk. Thank you, Samson.
Thank you very much for the kind introduction, and it's a pleasure to be here. So I'm going to talk about the logic of quantum paradoxes. My aim, since I suppose not everyone is particularly a specialist in quantum-related things, yes, it's a pleasure to be here. My aim is to talk about this, what I consider to be a fascinating subject, sort of somewhere between foundations of physics, computation, and logic, in a way that's hopefully accessible, will be reasonably accessible to everyone. In particular, I'm not going to presuppose particular familiarity with quantum theory. Okay, so what does one mean when talking about quantum paradoxes? I think there is a phenomenon that it does deserve to be studied under the heading of quantum paradoxes, but of course it seems quite strange. The reason we believe in quantum mechanics is that it works. It's our most successful physical theory, as is often says. It best explains what we actually observe. And of course, you can never observe a contradiction. At least I have no idea what that would mean. I think it's exactly what one can't observe, even in principle. So therefore, why do we speak of quantum paradoxes? And the reason is slightly subtle, and it's something we'll try to convey in various ways through this talk. It's because our observations, while individually consistent, if you take them together, jointly contradict reasonable assumptions that we have, which reflect a classical conception of reality. And that turns out to be important, not only as a fascinating foundational issue, but because it's also related to the possibility. Yeah, sure. Yeah, that's fine. Is it long enough to? Okay, well, I'll stay here. That's fine. Yeah, if I'm close enough to the microphone. Okay. So, observations are individually consistent, but jointly contradict the reasonable assumptions which reflect a classical conception of reality. Now, this turns out to be important also in terms of what quantum computing offers us, the reason that people are interested in it, namely quantum advantage. In other words, the idea that we can do computational tasks better using quantum resources than we could do using classical resources. Something that is not, one could say, well, that is an imperfectly understood phenomenon at the moment. But of course, there are exciting examples which lead us to believe that this is the case and which motivate the whole pursuit of quantum computation. Now, if there is quantum advantage over just doing classical computation, it must be based on the non-classicality of quantum physics. So understanding that non-classicality is exactly lies at the foundations of understanding what quantum advantage is and where it comes from. Now, so what are the features of quantum mechanics, broadly seen, if you like, from a bird's eye view, as of course confirmed by an enormous body of experimental evidence? So the crucial point is we cannot measure or observe all properties simultaneously. I've just said what we can observe in a single observation is perfectly logically consistent, otherwise how could we observe it? But we cannot measure all properties simultaneously. What we can do is observe certain subsets of properties which formally correspond to commuting families of observables. And these subsets give us a sort of, each one gives us a sort of observational window onto the behavior of the system. And if you look at these different subsets, they give us a family of such windows which overlap, but none of them tells us the whole truth about the quantum system. So in effect, what we can observe are partial views of the system, which, if you like, if you think of a number of variables and we're trying to find the values of those variables corresponding to the properties of the system, what we can observe are assignments to a subset of variables. And in general, there's no assignment of values to all the variables consistent with all of these windows. And if I say it like that, it may not sound so shocking, but from a classical point of view, it is shocking. We'll see in a moment. In a nutshell, summarizing this, contextuality arises where we have a family of overlapping pieces of data which is locally consistent but globally inconsistent. And this already, we find such terminology in things like constraint satisfaction and so on. It already, if we speak of consistency and inconsistency, suggests a connection with logic. So to illustrate this, and I think to give a useful visual image to go with this, imagine we're looking at a building, an imposing building in the distance, and we're trying to take pictures of it with a camera which has limited aperture, so we can only take pictures of parts of the building. And each of those parts that we can take a picture of looks perfectly reasonable in itself. And it's even the case that if you look at the borders between any two of those snapshots, they fit together in a sensible fashion. Right? So that's our locally consistent family of data. Now we would think, obviously, that all of these partial snapshots are simply parts of some global picture of the whole building. But if we try and put this together, what we find is what you may recognize as, I don't know how many people recognize this. This is the Escher ascending and descending. It's a visual paradox. If you follow the staircase, it's either always going up or always going down. So it's in ordinary three-dimensional physical space, it's paradoxical. Okay, so this is a clever, we can say the Escher painting is a clever visual illusion. But actually, this is a very good metaphor for what actually happens in quantum mechanics and what's telling us as at a most fundamental level, or at a fundamental level of description of nature, of physical reality. Now, this stuff is by now very well established. In fact, these phenomena of non-classicality officially joined the physics establishment in 2022, when pioneers for experiments on experimental verification of the kind of phenomena we'll be talking about received the Nobel Prize. So this was Alan Aspère, John Clauser, and Anton Zeilinger. And they were, what they were doing was experimentally testing the reasoning about non-classicality famously done by John Bell in the 1960s. If John Bell had lived longer, he died relatively early, he would no doubt have received a Nobel Prize, but this was awarded just 3 years ago, 4 years ago now. So what are these Bell experiments? By the way, how many people have heard of Bell's theorem? How many people could state and prove Bell's theorem? Well, in about 5 minutes, you'll all be able to do that. So that's where we're heading. So, so the idea is we prepare a suitable entangled state. We're not going to go into the details of what that is. We send part of it to Alice, part of it to Bob. Each of them selects some measurement, and we're going to do a number of these measurements. We're going to do many prepare and measure tests as part of this experiment, and we collect the outcomes of those measurements. And everything is nice and simple. We're just going to have 2 alternative measurement settings, and for each measurement, 2 possible outcomes, 0 or 1. And then we do a lot of these, and we look at frequencies of outcomes and collect the statistics. Now, that's the sort of physics experiment schematic for a Bell test, but there's a very nice way of looking at it in terms of games, which is very nice from a computer science point of view, because then we see it is really a sort of computer science kind of question that we're looking at. It's sort of an isomorphic description, is we have a game with 2 players, Alice and Bob. I mean, all of this generalizes, of course, in various ways, many players, many inputs, many outputs, and so on. But this is the most basic version. So we have 2 players, Alice and Bob, and an essential point is that Alice and Bob are not allowed to communicate with each other during the playing of the game. So we put them in separate rooms, we take away their mobile phones, we enclose the rooms in Faraday cages, or at a more extreme form, they're space-like separated, so there's no time for light to travel from one to the other while we're performing a round of the experiment. And there's a verifier who sends inputs to Alice and Bob, and then they produce outputs which the verifier inspects or collects somewhere, and then Alice and Bob together win the game if they achieve a certain level of coordination in their response. So in particular, the most famous version of this game, often called the XOR game, but it could also be called the CHSH game, Clauser, Horn, Shimoni, and Holt, which Clauser being one of the Nobel Prize recipients. So they're playing a cooperative game. Verifier chooses the inputs. Alice and Bob each have to produce an output. And the crucial point is Alice doesn't know, choosing her output for her input, which input Bob has received. So they can't coordinate during the play of the game. And we have this winning condition that looks a little bit strange at first sight, that the exclusive OR of the outputs, everything is Boolean here, 0 or 1. The exclusive OR of the outputs has to be equal to the conjunction of the inputs. This looks a bit odd, but if we spell it out and you think of the truth table for conjunction, what it's saying is on the 3 lines of the truth table where the conjunction is false, then the exclusive OR has to be false, which means that A and B have to take the same value. Either they're both 0 or they're both 1. So to put it in a snappier way, in 3 of those cases, the outcomes have to be correlated. They have to be the same, either both 0 or both 1. Okay, everyone happy with that? And in the 4th case, where the conjunction is true, then the exclusive OR has to be true, which means that the outputs are anti-correlated. If one is true, the other is false, and vice versa. Okay, so we get these cases that we see here. So if we think of some kind of probabilistic strategy for Alice and Bob, then all the success probability, the weight that we put on the winning conditions is going to be all on the cases either where the outputs are anything other than both true, the inputs are anything but both true, in which case outputs have to be correlated, the first 3 cases you see there, and then the final case, the outputs have to be anti-correlated. And I'm assuming here a uniform distribution on the inputs, often achieved in the experimental thing just by suitably randomizing the measurement settings. So a strategy, without sort of going, if we might think, how might Alice and Bob do something? Well, we can describe it by a strategy that just is a table tabulating these conditional probabilities, telling you the probability for any given value of the inputs of the outputs. So here is a table describing such a strategy. So here are the possible inputs. I've just treated them as sort of binary, as bits, 0 or 1. And you see in the first 3 rows, here is a strategy I'm giving you. So you see on each row, for each given value of the inputs, we're describing a probability distribution on the outputs, the joint outputs of Alice and Bob. So you see they're non-negative numbers summing to 1 on each row. So it's just a table of 16 numbers, but there's a lot of structure here. Just to be completely clear about what this is saying that the strategy is such that if the verifier sends Alice 0 and Bob 1, then with probability 1/8, that's the highlighted item, Alice outputs a 0 and Bob outputs a 1. So that's the column there. Alice outputs 0 and Bob outputs 1. So that's what that entry in the table is saying, and all the other entries have exactly similar readings. Now, from what we said about the XOR game, right, so then all the weight is on the correlated outcomes for the first 3 rows. That's either 0, 0 or 1, 1. So you can see on the first row we get a probability 1. On the second row, we get a probability 6/8 from the 2 correlated outcomes. And on the third row, we get probability 6/8. And finally, on the final row, it's the anti-correlated outcomes. And you see that twist. The fourth row is sort of, we twist things compared with the other rows. And this twist is a logical twist, it's a geometric twist, and it's a probabilistic twist, because we put the weight here in this strategy on the anti-correlated columns, where the outcomes are different. So if you just add all of these arithmetically, you get 3 1/4. If everything is uniform distribution, you get this value of 0.81, slightly more, in fact. Okay, so I showed you a table of 16 numbers. I've computed this value. I mean, should we be impressed or not? Well, actually, it turns out we should be impressed and surprised, certainly if we're wearing our classical glasses, because the optimal classical probability we could achieve, however clever we were going to be, but using only the resources of classical computation and information processing, the best we could do under these circumstances is to get a winning probability of 3/4. And here we have a figure that's more than that. Now, how do we, now it's very easy, as a first observation, to get a winning probability of 3/4. Does anyone have a suggestion for how we would get a winning probability of 3/4? But this is the thing. We said that the key condition in the game is that each one in a given round doesn't know what the other has received. So the only way they can form a strategy together is to agree beforehand, before they see any inputs, what to do. And so what they could simply do is to say, well, actually, I mean, they could very well say, if you get an input of 0, then output 0, and if you get an input of well, they could simply say always output 0, right, regardless of the input. And actually, 3/4 of the time, this would be correlated, and 3/4, well, sorry, it would always be correlated because they would always output 0, both of them. And 3/4 of the time, that would be a good answer, because in 3 rows, correlated wins. So therefore, they would get a 3/4 probability of success. So it's a very, very dumb strategy. But not only is that a particular strategy that gives you that value, that's actually the best you can do classically. And the fact that that's the best you can do uses, and is essentially the same as the use of Bell inequalities, which are the famous thing that come out of Bell's theorem and the proof of that theorem. So that table, may look just like some stupid table of 16 numbers. If it could be implemented, would be a very shocking thing under the stated circumstances, because it would exceed what we're just claiming cannot be. It exceeds the bound of what can be done using classical information processing. So it's showing that classical information processing is not the last word as far as our universe is concerned. So this is the first and most basic example, if you like, of quantum advantage in an information processing task. So what is this method of Bell inequalities, which is what is used to prove Bell's theorem? So Bell's theorem, if you like, has two parts. One is this bound on what you can do classically, and then the other, the observation that you can find quantum examples that exceed this bound. And just to say that this table can be realized with a suitable entangled state and measurements. I'm not going to go into details, but it's a simple exercise to do that. So rather than going into that, I want to look at this more general question, which is, there's this idea of Bell inequalities giving bounds on what you can do, what kind of correlated behavior you can achieve using only classical methods. And we can give a general answer of that. And as it turns out, this answer even answers a famous question from a pioneer of both logic and probability, namely George Boole from the 19th century, and his question on what he called the conditions of possible experience. Now, Booleans, Boolean algebra, and also, as I say, a pioneer of probability. So what I'm going to do is give a simple way of deriving this bound so that we can see directly how this table we were just demonstrating exceeds it. And this needs nothing more than a little propositional calculus and a little probability. So just to generalize it a bit, suppose we have some propositional formulas which we can think of as describing events. We have some basic variables and then we combine them using the usual Boolean operations or propositional calculus formulas, and we're able to assign a probability to each of these formulas. So a priori, if I tell you nothing more than that, then all I know is that these numbers, pi, are numbers between 0 and 1, they're probabilities. But now I'm going to give you one additional piece of information about this situation, which is of a logical character. I'm going to say these formulas are not simultaneously satisfiable. That is, there's no way of setting the values of the variables that make all of them true. And this ultimately is going to relate to this idea of this twist that we already looked at. But anyway, we're just saying the formulas are not simultaneously satisfiable, which means that any n-1 of them must imply the negation of the remaining one. Okay? Which by contraposition means if the nth one is true, then one of the others must be false. Now we can use a little probability. So we have assigned a value, a probability value to each of these formulas. So because of the fact that probability is monotone, the probability of a smaller event is less than or equal to the probability of a larger one. We get this first inequality. The second inequality is actually known as Boole's law. We're not making any assumptions about disjointness. We're just saying the probability of a union is less than or equal to the sum of the probabilities. It's a very simple probabilistic inequality. Of course, you can have double counting and so on, which is why it's usually strictly less. But anyway, it's a basic law of probability that the probability of a union is less than the sum of the probabilities. Now, the probability of a complementary event is 1 minus the probability of the event. And so if we just tidy up a bit, what we end up with is, from the assumption that the formulas are not simultaneously satisfiable, we end up with this numerical inequality, that the sum of the probabilities is bounded by n minus 1. Okay? So is everyone happy with that derivation? Because we will derive interesting consequences from it. In fact, we can come back to our table. Again, let me make the point, this is a table that exists in physical reality because it can be obtained from quantum mechanics by using a maximally entangled state and suitable choice of measurements for Alice and Bob. So even if Alice and Bob are space-like separated, we sort of went through the thing of, with our experimental schematic, we would generate these, we would get frequencies, and it would sort of lead to these probabilities. And this is exactly the kind of thing that is done experimentally with Bell tests. Okay, so now let's look at it from a logical point of view. What I've now done is highlight the winning positions, winning events, winning outcomes, which are the correlated outcomes on the first 3 rows, as we already said, and the anti-correlated outcome on the final row. Now, if you look across each row and you take the event, what does correlated mean? It means either both the variables are true or they're both false, which is the same as saying if and only if of the 2 variables. So we get these if and only if statements to describe the winning events on the first 3 rows. And then when we have this twist on the final row, the anti-correlated, this is just the exclusive OR of the 2 variables. Now, what I'm going to claim is that these propositions are mutually contradictory. They're not simultaneously satisfiable. They can't all be true. Let's just see this very easily. If we start from A2, A2 if and only if B1, we can replace it by B1. The first line, we can replace B1 by A1. The second line, we can replace A1 by B2. And now we have B2 exclusive or B true, which can't be true. If you may recognize this as a kind of liar cycle, where you have a chain of things that lead you on eventually to the negation of where you started from. Anyway, the fact is these are not simultaneously satisfiable. So by the simple result that we just had here, if we sum the probabilities of those events, we would get 3, a bound of 3, right? Because there are 4 events, so it's n minus 1, so the bound would be 3. But what we actually found, or actually find, looking at this table, is that we violate this inequality by a quarter. So that's that's how we can apply a kind of Bell inequality of this particular logical form to show the bound that we were mentioning. So obviously 3 divided by 4, if we taking uniform distribution on the inputs, would give us the 3/4 that we were mentioning earlier. And here we have a table that violates it. The general version of this, slightly more general, I don't have to worry too much about this, but we can generalize from saying just that the formulas are consistent to saying they're k-consistent, meaning that the largest number that can be made true is k. So we had before, we were assuming just n minus 1 out of n, but it could be some smaller number k, which would give us a sharper Bell inequality. In a similar way, we can derive that if we assume the family is k-consistent, that the sum of the probabilities is bounded by k. And in fact, perhaps surprisingly, one can show that all Bell inequalities arise in this way. This gives a result coming from this. Okay, if I don't know if online, hopefully online people can hear me now. Okay, so in fact, as I was mentioning, this is a nice story that connects George Boole from the 19th century with John Bell from the 20th century. George Boole was a pioneer of logic, probability, and we can say of computer science. There's a remarkable connection between his work from the 1850s and the idea of Bell inequalities, fundamental to Bell's theorem in the 1960s. And this was first pointed out by the philosopher of science Informatics. So what I'm talking about is there was a volume in tribute to Itamar, who passed away some years ago. So in his very nice summary of Boole's problem, we're given rational numbers that indicate the relative frequencies of certain events. If no logical relations obtain among the events, the only constraints imposed on those numbers are that each be non-negative and less than 1. However, the events are logically interconnected, there are further equalities or inequalities that obtain among the number. The problem is thus to determine the numerical relations among frequencies in terms of equalities and inequalities, which are induced by a set of logical relations among the events. The equalities and inequalities are called conditions of possible experience. He was perhaps using a sort of Kantian-sounding terminology perhaps in a semi-humorous way. Anyway, it's a beautiful question, and really it translates directly into the situation we were looking at. We have these events which can be described by propositional formulas. We're given the probabilities, and we're asking what numerical relationships between the probabilities can we infer from the logical relationships between the events. And the result I just mentioned here, coming from this work with Lucy and Hardy, is giving, I would say, a full answer to that question, because we're saying all the general probabilities that hold among the events follow from this single logical principle. So classically, we have these conditions of possible experience, but as we've seen, quantum behaviors can exceed this. So in some sense, what we're searching for are the quantum conditions of impossible experience. Actually, it's with this nuance that what we see in our classical window of observation is still going to be possible. It's when we try and fit it all together that we get some such impossibility. Well, we want to, if one is a sort of theoretician, one wants to abstract from this and get a general description which will apply to all such phenomena, or a very large class of such phenomena, which is what I did in work with Adam Brandenberger some years back, which has been, various colleagues have developed a lot since then. I'm not going to dwell too much on the connections here, but the idea is we saw a particular example of a table, and we can generalize very widely beyond that particular example. So we just have an arbitrary set of measurements, we have sets of those variables that can be measured together, and we have outcomes, for possible outcomes for each of the variables. So that gives us a kind of type of the situation, which we can call a measurement scenario, and then we can populate this with actual observed behavior, what we call an empirical model. We call it an empirical model because, in principle, if you can prepare systems and perform measurements and observe the outcomes, then you can collect these statistics empirically. It's observable behavior. And the what we refer to as local consistency shows up here, in that if you take any two of these observations, they're consistent with each other in the sense that they agree on their overlap. In the same way that we saw with the picture of the tower, we took two of the snapshots, you look at where they overlap, it's all is in agreement. So formally, this would be that these distributions on the larger context would restrict in a well-defined way. So for example, if you took the intersection of two contexts, then the marginals coming down from any two of the descriptions to their intersection would agree. Okay. Now, in that setting, we can define what contextuality is. So in that setting, where we do have a global description of the phenomena which accounts for everything, a picture of the whole building, which we could then project down to the things we can directly observe, then that would be a classical explanation which would account for everything we can see. So formally, this would be a distribution on over assignments to all the variables, which would project to give us each, or marginalize to give us the observable distribution for each of the contexts. So we can use some geometric terminology here. This is a question about local and global. The local situations are the directly observable things. And we're asking, is there a global description which projects down onto each of the locally observable descriptions? So in that geometric terminology, we can speak of global sections. And if that does exist, then we can say that the system is non-contextual. Everything has a meaning independent of which observational window we're looking through. It all fits together, and in principle it could all be described classically. In fact, this is equivalent to another way of attempting to give classical explanations known as hidden variable theory. So we can think of this as a kind of canonical hidden variable theory. So in the case that such a global section exists, then the system is non-contextual. Nothing to see here. In the case that it does not exist, then we have the phenomenon of contextuality. And thus we see indeed that contextuality arises when we have a family of data which is locally consistent but globally inconsistent. And the import of Bell's theorem and similar results, and there are many by now, is that there are empirical models arising from quantum mechanics, real, things that can be experimentally verified, which are indeed contextual in this sense. Now, a nice aspect of this is that we've already hinted at, is that there's a sort of geometric or topological way of looking at this. So I think it will be nice to develop that a little. So here I'm giving another example of one of these systems which is contextual. This is what is often called the Hardy paradox. Again, the notion of paradox here. And here we don't even need probabilities to make the point. I only put in, so I've just, instead of looking at probabilities, general numbers between 0 and 1, I just put in sort of I just distinguish between impossible and possible. So impossible is a cross, marked with a cross, that means probability 0, and a tick is anything above 0, so therefore possible. Now, we can depict a system like this by a kind of discrete bundle. So we have a kind of base of the variables that we're measuring, and above each of the variables we have, if you like, a fiber with the possible values that variables can take. I mean, everything's very simple. We have these 4 variables, and each fiber is 0 or 1. And we put an edge between 2 variables in the base if they can be measured together. So the idea here is any Alice measurement can be combined with any Bob measurement. So we have AB and AB prime, and A prime B and A prime B prime, but we don't have an edge between A and A prime. And similarly, we don't have an edge between B and B prime. This is the point kind of started off with, that we cannot measure all variables together. That's what creates the space for these quantum paradoxes to arise. And now we can put in the model itself, we can put in edges in the fibers, where the edges correspond to possible combinations of outcomes. So you see that in the first phase, the thing over AB, all combinations of values are possible. So we put in all the possible edges there. But in each of the other 3 rows, 3 combinations of outcomes are possible and 1 is impossible. So we have to omit one of the edges on the other 3 faces of this little cube. Now, we can then say, can we find a way, what is a global description of such a behavior? Can we find a way of setting values to all the variables which is consistent with what's allowed in this model? And geometrically, this translates into, is there a closed path that goes around visiting each of the variables once and consistently assigning it a value? And we see within this model there is indeed such a thing, as is marked in red. So far, that local possibility of getting 1-1 in the face that we see between A and over AB does extend to a global description. It makes sense in terms of a possible actual value possessed by all the variables. So far that looks non-contextual. But now let's choose instead this other possible behavior over AB, namely that of 0, 0, the one you see and the combination you see with the red tick in the table. So now our task is, can we find a path that goes all the way around and sets each variable to a unique value and comes back where it started from? It's a sort of consistent description. Well, you see that there's only one way we can go from here, say going on from B. We only have one option, which takes us to 1 there over A prime. And then again, we only have one option, which takes us to 0 over B prime. And again, we only have one option, which takes us to 1 over A. And you see, we haven't come back where we started from, which means we have an inconsistency. So locally, we do have an inconsistency. We have an inconsistency in the sense of no global description accounting for this local observation. And this is the sense in which we speak of the Hardy paradox. So this is just showing that if we go around the other way, exactly the same thing happens to us. And in fact, there's a hierarchy of such forms of contextuality. So the Hardy paradox does have some consistent global descriptions, but as we just saw, for some particular local possibilities, there's no way of extending them to a global assignment which accounts for that local possibility. But there are more extreme forms of contextuality, and the thing to the right, you can see immediately, visually, that wherever you start, if you go around, you don't come back where you started. In fact, you have to go around twice as it happens. And it's not too hard to see that this is closely related to the Liar paradox, or extended version of the Liar paradox. You could also say that it's a kind of discrete version of the Mobius strip. You have a band and you twist it, and then sort of somehow you go around and you don't immediately come back where you started. In fact, this is a known example it's closely related to the CHSH inequality or that game, the XOR game we were looking at earlier, because here we're just putting all the weight on the winning positions, taking the possible edge relations from those weights. So it's the correlated things on the first 3 rows translated to the parallel lines over the front 3 contexts, and then the twist becomes literally a twist on the back face. So it connects the CHSH inequality, this discrete Mobius strip, and the logical paradox. So I'll use it as an illustration that we get this beautiful connection in this subject between physics, probability, logic, and topology. And I mean, obviously, I'm just showing this in the form of a visual illustration, but let me say that if one goes into it, there's a lot of precise, beautiful things that come out. Sort of geometric point of view, we think the fibers vary over the base factorially. Data is given by distributions over the events. Incidentally, this mathematics, let me just mention, a pleasing feature of this is, apart from the developments in quantum theory, the formalism also applies to many situations of a broader nature, things in databases, and recently now there's a lot of related things happening in machine learning and consistency notions there, local consistency, global consistency. So we find similar formal structures arising there. So this fits perfectly into the language of sheaf theory, which is all about the mathematics of the passage from local to global and obstructions passage. You can use ideas from terminology to which sort of concepts characterize the twisting of the fibers. They relate to logical paradoxes, as we hinted. But then there's also on the quantitative side, where we saw the Bell inequalities, there's a resource theory of contextuality and notions of simulation. Key measures of contextuality, such as the contextual fraction, connections with logic and computation, database theory, constraint satisfaction. And as I was saying, increasingly with things, even quantum error correction, and also sort of machine learning and reconciling consistent and inconsistent information in knowledge systems, and the yeah. Okay. Do I have 5 minutes? Or yeah. Okay. So well, I hope this has been at a reasonably understandable level till now. I mean, I thought I would mention, since I'm talking about logic and quantum paradoxes, that the very same ideas are reflected in a more explicitly logical format. I'm sure many of you will have at least come across the idea of quantum logic, which, and there's a sort of a preferred version of that which I prefer, which very nicely illustrates also this idea of the logic of quantum paradox. So let's go right back to John von Neumann. John von Neumann was a mathematician, but it was he who cast ordinary quantum theory, we're not talking about quantum field theory, but basic quantum mechanics, in a definitive mathematical setting which is still being used to this day, in a book that appeared in its English form in 1932, Mathematical Foundations of Quantum Mechanics, in which he identified quantum properties or propositions as projectors on a Hilbert space. We don't need to go into the technicalities. Projectors correspond exactly to the closed subspaces. The other person shown in the picture there, von Neumann, is the one on the left. The one on the right is Garrett Birkhoff, renowned for his work in lattice theory. And after this, Birkhoff and von Neumann wrote a very famous paper, The Logic of Quantum Mechanics, which proposed the lattice of closed subspaces as a non-classical logic to serve as the logical foundations of quantum mechanics. And it's had a mixed, the most notorious thing about this compared with ordinary logic is the distributivity failures, which is quite unpleasant. Now, there's a sort of critique that one can make, and that was made, as we'll see later in just a moment, that what does this mean operationally? You see, if you have closed subspaces, it's certainly true that the intersection of them is again a closed subspace. But if I have projectors describing, given projectors describing a subspace, they only have a meaning together operationally if they commute. So what is the operational meaning of this conjunction when the projectors don't commute? It's not, one might question whether that's such a good thing to do, to take advantage of that tempting connection between projectors and closed subspaces. So this led to an alternative approach by Kochen and Specker, who have a very renowned paper from, again, just after Bell's paper, which really founded the whole topic of contextuality, the paper, The Problem of Hidden Variables in Quantum Mechanics. And they used, rather than these quantum logic structures, orthomodular lattices, they used partial Boolean algebras. And the idea is they only admit physically meaningful operations, I should say. So they now represent incompatibility, the fact that projectors don't commute, by partiality. So rather than, so non-commutativity bubbles up in various ways in different formal expressions. In the Birkhoff von Neumann quantum logic, it bubbles up as non-distributivity. In the Kochen and Specker approach, it manifests as partiality. And in a later paper, Kochen gave a rather beautiful development of how to reconstruct quantum mechanics in a logical way in this framework. There's actually a flaw in his account, which I'm still trying to fix up, but that's another story. So I just want to give a small flavor of this. So what is a partial Boolean algebra? Well, you have a compatibility relation, which, you know, with projectors would be, do they commute? And then the usual operations of and or are now partial, with domain only the compatible operations. And then there's an important point that if you have a set of pairwise compatible elements, you can always close them up under the operations to get a total Boolean algebra. And these are the windows. Algebraically, this is a model of our observational windows in which everything looks perfectly classical. It's a window where everything is compatible, so things you can speak about all together. And the canonical example of such a thing are the projectors on a Hilbert space. So conjunction typically, which is the product of projectors, which corresponds to the intersection of the corresponding subspaces, becomes a partial operation defined only on commuting projectors. Okay, and now we can state the form that Kochen and Specker gave. You need that the Hilbert space has dimension at least 3, and then turns out to be a canonical way of stating their result is that there's no way of mapping this homomorphically into the 2-element Boolean algebra, giving everything globally a value of true or false in a way that's consistent with all the conditions imposed, that preserves all the operations. There's no assignment of truth values to all propositions that respects the logical operations on jointly testable propositions. So we only need to preserve conjunction of things that are compatible because it's only defined on things that are compatible. So this is, okay. So really we're back to the conditions of impossible experience. And I think well, they essentially themselves stated an equivalent version, which I think says very clearly what logic quantum paradoxes is all about. So this is a way of talking about really the strongest form of contextuality, and we can say that, in fact, that it's equivalent to say that this partial Boolean algebra has this Kochen-Specker property. There's no two-value morphism, and to say that there's a propositional contradiction and a way of assigning values to the variables inside this partial Boolean algebra such that the structure satisfies this formula. So remember, a propositional contradiction is something where it's the opposite of a tautology. It's something where no matter how you assign values to the variables, the formula evaluates to false. So the simplest example is A and not A. That's not going to be an example of one of these phi's, by the way. It's not quite as simple as that, we'll see in a moment. But, you know, there are many other contradictions. So a contradiction, well, you know, it's manifestly absurd. How could that be? And yes, it is true that if you assign, that you can find contradictions such that if you assign values to the variables in these projectors, in these basic physical operational properties of quantum theory, it would evaluate to true. Which immediately tells us that this event algebra of quantum mechanics cannot be interpreted globally in a consistent fashion. Our local observations, which are real observations of real measurements, cannot be pieced together globally by reference to a single underlying objective reality. The values that they reveal are inherently contextual. How can the world be this way? Well, philosophers and others are still continuing to debate this. One of the fascinating things with quantum computing is that we can see ways of turning this, as they say, from a bug into a feature, where it turns exactly into instances of non-classicality on which we can leverage quantum advantage. Now, some of you will be familiar with non-classical logics, and I want to make a comparison between this quantum logic fact and, well, the most familiar non-classical logic of constructive mathematics, presented as intuitionistic logic, because it's very familiar there that the semantics of intuitionistic logic lets us falsify tautologies. So the simplest tautology is A or not A. The trouble with A or not A is that we may assert it, but have absolutely no idea whether it's A that's true or not A that's true. We just know that one of them must be true. So it's the essence of, if you like, of non-constructive reasoning. So of course it's a familiar fact that in the semantics of intuitionistic logic we can falsify such tautologies because we only want to keep the things that we can defend in terms of constructive information and witnesses and so on. Now, but in fact, while that's true about tautologies, when it comes to contradictions, intuitionistic logic is completely conservative over classical logic. Every classical contradiction is an intuitionistic contradiction. So Van Dalen was mentioned in our earlier discussion. I mean, so it's a simple point if you're going to the technicalities. But the point is that any classical contradiction cannot be satisfied in any sound semantics for intuitionistic logic. This is part of the asymmetry in intuitionistic logic. It's sort of, you don't have a classical duality, so you can falsify tautologies, but you can never verify contradictions. But as we've just seen, in quantum, we can verify contradictions. So in this sense, we can say that the logic of quantum paradox is more non-classical than intuitionistic logic, and if you like, is more shocking to our intuitions. So let me just finish up with, there's a subtle point which remains open of characterizing those contradictions that can be satisfied in partial Boolean algebra. So, one can show that there are contradictions that can't be satisfied in partial Boolean algebras, but some can. And it would be nice to give some characterization of which can. That's a question I've raised a while ago. Neil Shah and Anuj Dawar in Cambridge have studied this from the lens of computational complexity. So you can ask a kind of satisfiability problem for formulas. Can they be satisfied on a partial Boolean algebra, in particular one of these quantum partial Boolean algebras of projectors? And using sort of other results in a suitable way, they can show that if the dimension of the Hilbert space is arbitrary, this is an undecidable problem. And if you fix the dimension of the Hilbert space, it's in a well-known class of the existential theory of fields, existential theory of real closed fields, which is a very natural class for many geometric problems. It's basically saying, can you find a list of numbers that satisfy some polynomial equations and inequalities? So it comes up a lot. It's known to be in P-space, but it's conjectured to be a separate complexity class within P-space, and they can show for fixed finite dimensions it is complete for that class. And there are many other fascinating questions I don't have time to go into that we're currently looking at. So let me finish up by saying that I've had the pleasure of working with many great colleagues, students on this. So here are some of them. In particular, the sort of approach I've been describing started off in work with Adam Brandenberger, and the work on the logical Bell inequalities was done with Lucian Hardy, who's also the author of the Hardy paradox. And much of my work has been done in collaboration with Shane Mansfield and Rui Barbosa, who the next two shown there, and many other great colleagues. And if you do want to look at, as I said, this all, I've sort of spared you the details, as it were, but if you're interested to go in more depth into some of what we've been talking about, there are plenty of references. So anyway, thank you very much for your attention.
Hello. Okay. Thank you very much for the talk, Samson. We have some time for Q&A. So if there are any questions, yes.
So in constructive logic, we have this duality between proofs and programs. Is there any such duality between any of these quantum logics, or a different quantum logic and quantum computation?
Yeah, well, we have a correspondence. I mean, I wouldn't call it a duality, but we have a correspondence between Curry-Howard, essentially. Yeah, good question. There isn't. I wouldn't say there is such a correspondence for quantum logic or partial Boolean algebras. On the other hand, there are type theories for quantum computation. So these type theories are used in developing quantum programming languages and their semantics. A lot of work on this has been done, for example, by Vladimir Zamgiev, building on early work by Peter Selinger and others. In another way, you can take the string diagrammatic calculi as formal calculi for quantum mechanics, are things like the ZX calculus, and some people may have seen the Dodo book of Bob Cooker and Alex Kissinger. But it's a good point. I would not say there was exactly a Curry-Howard correspondence. Yeah, the thing is that the Curry-Howard correspondence is where you have, I mean, it's sort of the proofs as programs. That isn't the way, I mean, actually, I do have an old paper with Ross Duncan, which does develop a kind of type theory of this kind. But it's turned out that, you know, the string diagrammatic approaches have been, you know, have been the things that really took off. That happened a bit later. Yes, it would be interesting to reflect on that. I think the closest that I can think of are these type theories developed for the purpose of semantics of programming languages by Vladimir and others. Also, yeah. But since you mentioned duality, let me mention that duality in the sense of something like stone duality has been, with Rui Barbosa, we have developed a duality for partial Boolean algebras, atomic partial Boolean algebras, which is somewhat remarkable because what the Koch and Strecker theorem in the form I gave it was saying is that there are no two-valued homomorphisms, hence there are no points. So it's a perfect example of pointless, you know, sort of they have no points in that formal sense. So there's no possibility of building a kind of space in the usual sense that you can build the partial Boolean algebra back from. And what we were able to do was instead to use the kind of Tarski duality for atomic Boolean algebras that correspond to sets. And the interesting thing is you replace sets by graphs, where the graphs come from this compatibility relation. And then we do get a duality between graphs and atomic Boolean, partial Boolean algebras. So I think that has been because people have been looking for non-commutative forms of duality for a while, then I think this is an interesting first step in that direction.
Other questions?
Thank you, Professor, for the interesting talk. From the outsider's point of view, I have a question. So would it be fair to say that the quantum advantage would arise precisely at the point that the global sections will fail? That means there's no global model that is consistent with all local observations.
Yes, indeed. So I could have, you know, done the whole talk about that sort of thing, but yes, you're basically, well, okay. We have to be a bit careful because we don't have a complete picture of quantum advantage. But for example, there's a beautiful result originally due to Robert Rausendorf, who's one of in what's known as measurement-based quantum computing, where he directly linked the possibility of quantum advantage in terms of the success probability of your computation to the presence of one of these kinds of contextuality. And you can make this more quantitative, which we did in later work, and we're sort of actually recently doing some more work on that. So there you see a very clear relationship between the presence of this non-classicality, this, as you say, this failure of a global section, with the possibility for quantum advantage. Another example of such a result is a very well-known paper by Mark Howard et al. On which, under the title "Contextuality Supplies the Magic in Quantum Computation," and this refers to so-called magic state distillation, where you need to add something to a sort of relatively tractable class of gates in order to achieve quantum universality, and you have to have contextuality there in order to do that. So that's a second example, and the third example is been fairly recently some beautiful unconditional separation results, because remember that although we have Shor's algorithm, we don't know for a fact that prime factoring is not in polynomial time. I mean, people will be surprised, but it hasn't been proved. But we have, for circuit families, we have an unconditional separation between shallow classical circuits and shallow quantum circuits. And the way that those examples are constructed uses exactly these kind of contextual models as the sort of seed from which you construct the appropriate family of circuits to show this quantum advantage. So that's three clear-cut settings where exactly what you're saying is the case. Now, what would be really nice is to have a single theorem from which all of these would be examples. So that's where we would like to get to. But yeah, there's every reason. I think what you say is what my understanding and belief is, and we have partial results in that direction. Yeah,
thanks. If I may have a follow-up question, so I'm from a machine learning background, and I think the topic contextuality that described here is kind of similar to some machine learning problems where we cannot have a shared representations that work for different tasks. So I'm not sure if you think that this is a kind of limitation of classic machine learning models, or if you think that this is some feature of like a quantum system that can exploit or help to resolve this kind of problems.
Again, a good question. I mean, there increasingly have been papers that are even using explicitly some of the tools we've developed for contextuality to talk about limiting bounds on rating some refinement of the contextuality we're studying to learning at a distance, sort of propagating information at a distance in a neural network, other things to do with local consistency and global consistency. So increasingly, this kind of structure is showing up in machine learning situations. So that's something that I think would be interesting to understand further. So I think it's quite likely, because the general idea of local consistency and global inconsistency does not depend. I mean, it arises in quantum mechanics extremely interestingly and importantly, but it isn't limited to that setting. And actually, there are close connections with things that have been studied in classical database theory. And actually, some of this work has led to some database theorists getting into this subject and, doing some very interesting things in connection with that. So I actually have a paper, I'm particularly proud of the title, Relational Databases and Bell's Theorem, because it shows that there's an isomorphic situation there, which has actually been studied by database theorists. So there was a famous debate. Anyway, so that's not really what anyway, there are things outside quantum where the same considerations, the same kind of structures appear. And then indeed the question is it a purely limitative thing, or is it something we can somehow take advantage of in building better systems? I guess that's the thing that it would be particularly interesting to clarify. Yeah, thanks for the question.
Thank you. Any other questions? Maybe we have time for a short one. Okay. Professor, we'd like to thank you again for this very exciting talk. And we'd like to invite everyone for drinks and coffee and snacks at the back, so everybody's welcome. So thank you again so much.
Understand this bit about Bell's theorem and classical database. I mean, what is